Hey there. I thought it would be useful to show you the alternate method, which is essentially the same as the method that Delta Math was showing you for finding related rates of change. And I'll use this same problem that we just went over using my, reciprocal fraction sort of form, just so you have more than one tool and you choose which method you prefer for finding derivatives. So here I'm just going to repeat the formula that we already found for the area of the shaded segment. We already found that in the last screencast, the last time we worked on this problem. Sorry. All right. Oh no. Gasp. Okay, I solved that problem. Okay, so we had said that area of that shaded segment is 12.5 times theta minus 12.5 sine theta. All right, and what we just said was it's the area of the segment of the circle minus the area of that triangle. That'll give us that shaded area. Okay, so look, if we want to take the derivative of both sides of this, we're going to get exactly what's asked for. It's a little bit more straightforward, to tell you the truth. So remember, they've given us d theta dt, right here, that equals 0.2. Our radius is fixed at 5. And we are trying to find the rate at which the area of the minor segment formed by the chord AB is increasing. So again, we had to find dA, area of this segment, dt. Previously what we did was we sort of messed around with these fractions and canceled some things with multiplying by the reciprocal of some fractions. But I'm going to tell you right now, what we can do is simply take the derivative, and I have not shown you this before, and I'll see if I can come up with another example after this, so you can see another example, but take the derivative with respect to t of both sides of this equation. All right, so I'm going to put this in brackets and this in brackets, and we're going to take the derivative with respect to t of both sides. Now, if you're taking the derivative with respect to t of a, that is dA dt. Now here, we are going to say that the derivative of 12.5 theta, well, if this theta were, well, it is a variable, right? So that's going to equal 12.5 times whatever the derivative of theta is. So, with respect to time. You get that? So we're taking d dt of theta. That's what we just did here. Ah, okay. And so now, let's do the same on the other side. Not the other side, but the next thing. And we're going to have minus 12.5 cosine theta times d theta dt. All right, and this is just using the product rule, I guess, sort of, or just using regular derivatives. Now, guess what? We're trying to find dA dt, and this is pretty straightforward. Because we were already given d theta dt, we're trying to find out when theta equals 1. So let's just substitute our numbers in. 12.5 times d theta dt, which is 0.2, minus 12.5 times the cosine of, whoops, not theta. Oh, it's supposed to be when theta equals 1. So times the cosine of 1 times d theta dt, which is 0.2. All right, and guess what? That equals that same number that we got before. Ooh, let me flip back. Which is approximately 1.15. And make sure that you use the correct units since we're talking about area. We're talking about square centimeters per what time are we talking about? Per second. per second. All right, I'm going to follow this up with another example similar to this so that you have a better grasp on it if you don't already. All right, now let me just show you another example where we've actually got two different variables. So we have this 3-variable formula for volume, and we can still take the derivative, differentiate both sides of that equation, and get find what we're looking for. Take a second to read this. Okay, and now let's just draw this diagram. So first thing I'm going to do, right there, cone. Cone. The radius is decreasing. Okay, so we've got to use negative value here. Is decreasing at a constant rate of 5 centimeters per minute. So what we're saying, what we're being told is dr dt, the radius, the rate of change of the radius with respect to time is -5. I'll write that down. Volume is decreasing at a rate of 148 cubic centimeters per minute. So that means dv dt is negative 148. Now, at the instance when the radius of the cone is 2 centimeters and the volume is 21 cubic centimeters, what is the rate of change of the height? So question, what is dh dt is what we need to find out. Now, here's what we're going to do. Oh, sorry, dh dt when, sorry, r equals 2 and v equals 21. Oops, 2 and v equals 21. Uh-oh, I can't find my eraser. Now, here's where we're going to use the equation for volume to figure out, sorry, I just had an interruption. And we're going to differentiate both sides. The reason why this is going to be helpful is because we have two variables in our volume formula. So volume is pi over 3 r squared h, right? Pi over 3 r squared h. Here's what we're going to do. Since we are looking for a derivative with respect to time, we are going to take the derivative with respect to time of both sides of this equation. Now, since we have, I'm sorry about that weird funky thing on the right side, since we have two different variables, we're actually going to have to use the product rule here. So look at this. On the left side, the derivative with respect to time of v, of the volume, is dv dt. All right. And here we have pi over 3, dooby-dooby-doo. Let's factor that out. Pi over 3 times, now let's take the derivative of this guy right here with respect to time. This is going to require using the product rule. All right, we have two sort of different things, different functions being used. So the product rule, I'm going to take the derivative of the r squared, so that's 2r times the other function. Since we took the derivative of this is being multiplied by dr dt. Okay. Using the product rule again. Oops, let me put that in brackets. Now we take the derivative of the second variable, which is h, times the first expression, I guess. So r squared times the derivative of h, which is 1. Since we took the derivative of h, dh dt. Now guess what? We have a whole lot of these things, and we can substitute numbers right in. Ooh, I think I need to extend my screen. Hang on. Okay, so we have, I hope I can write on this screen. dv dt, we know dv dt is -148, so substitute the numbers that we have been given. Pi over 3 times 2, r, we're given r at the moment when r equals 2. So 2 times r is 4. Uh-oh, we had to find the height given that volume. Hang on one second. Let's find the height given the volume. So if dooby-dooby-doo, sorry. You take a second to do that. I'm not going to waste your time. Okay, I just calculated the height is 63 over 4 pi. I may be wrong, but that's would not be unusual. 4 times what? 63 over 4 pi. We can see this and this and this and this cancel. Times dr dt. We were given dr dt. It's negative 5. So times negative 5 plus, what is our r? 4 times dh dt. Ah, that's what we're looking for. 4 times dh dt. Alrighty then. So what are we left with? We're left with, and I'm sorry this is getting messy, negative 148 equals 63 over 3, that's 21 times 5, which is, sorry, 105 plus 4 pi over 3 dh dt. Now, solve for dh dt. Okay, I'm sorry, there's a transcription error here. That's actually supposed to be negative 105. When we solve for dh dt, you're going to get negative 10.3 approximately. And so, once again, this is an alternate method for finding a rate of change based on other rates of change. We can just take the derivative with respect to whatever you're looking for, in this case, respect to time, usually it is, of both sides of your formula. Okay, go off and conquer. Toodaloo.